next speaker is Mark Berkowitz, who is from SQL Stream Incorporated. It is, he's going to be talking about infrastructure for the streaming data problem. Lots of us machine learners who are working on streaming problems could make use of some of the infrastructure, I think. Seems like a pretty cool product. His background is he got his bachelor's in physics from UC Berkeley, and he worked in the financial industry for a while. And without further ado, please tell us about SQL Stream.
Thank you, and thanks for inviting me to this conference. So I'm an engineer at SQL Stream, the company, which makes SQL Stream the product, which is a platform for streaming analytics. But I'm going to be talking about a particular application of this, a particular in seismology, specifically a joint project that we did with a consortium of universities, specifically UCSD. So I'll briefly give the background and sketch out the problem, and then I'll spend about half the time talking about SQL Stream, explaining what it is and what it does, and then I can go a little bit into the details of the solution. So I'm kind of an outlier here today because I'm not talking about machine learning at all. I'm talking about infrastructure, a specific programming platform for doing computations on streams on a single client server system or in the cloud. So the background is there's big science. There's a large consortium called the OOI, Ocean Observatories thing, NSF founded, involving various institutions, academic institutions in the country. And the idea is to provide a kind of enormous cloud workspace for fostering research and publicizing the results of research. And a little piece of this is called the OOI-CI, which stands for Cyber Infrastructure. And it's basically a private cloud that's being built up so that experimenters can share data and share networks of sensors and provide an application computing platform for doing stream computing. So here's their slide, and it's much better than anything I can draw. And you can see from the logos at the bottom that this is well sponsored, a lot of institutions involved, and it's very large scale. So a lot of work's going, it's a long-term project, and this infrastructure is being built up. Well, we got involved doing an application to plug into this about 1.5 years ago. So at that stage, there weren't many tools to make this an easy thing to build an application on. There are the usual open source components are available. There's great use of AMQP, which is an open source message bus with a Java bias, and a lot of the experiments are done by just experimenters writing their own Python code. Well, where we're coming from in our company is we're trying to provide a kind of a middleware platform where it's easier to develop streaming applications. Now, our focus is really on the commercial world, and our particular take on this is that SQL, the database language, is familiar to commercial applications, and they would be in the situation that they would have some kind of batch-oriented database application, and they just couldn't cope with the new world of streaming data. So this would be an easy transition for them. Nevertheless, we met people some scientists who were working on a project here. So I'm looking at our platform more abstractly, that we have a higher level language, some of our abstract for describing a computation. And as an experiment, we were just asked to help build a little piece of this. I think what was happening was that there was an existing system using proprietary software, and they were trying to detect earthquakes, and they wanted to adapt this to fit into this generic infrastructure. And so we proposed that we could help do it. So now quickly into the background of the application. the general point is to detect meaningful events in seismographic signals. And eventually there'll be a large worldwide system of sensor grids of all different kinds, mostly on the ocean floor. But at the time that we built this prototype, what was available is this array of ground sensors. So I don't know if this is accurate or just suggestive, but there's a regular grid of ground stations which have seismographs, and each of these has at least one sensor that produces at least 3 signals of vibration in the ground. So the idea is that you get signals. So each horizontal strip is one time series signal from one channel from one sensor. It's the blue line, and the point is to find a burst that's meaningful, that's a candidate for being due to an earthquake and not just noise, and to bracket off the interesting part. So the first stage is just to detect meaningful events in this sense. So this is sort of pattern recognition, but there was a prescribed algorithm which is based on the physics of the situation, and our challenge was to do that. So actually so the idea here is that these are related. This is sample data, this is a meaningful thing, and you can tell that it's detected. The trick is to find the onset is not the middle of it. It's the red dot with the vertical line, and then there's a cutoff point, which is the second vertical line. And all the little yellow dots are false end transitions that the algorithm has eliminated. So the first stage is given many channels of data like this to find significant events. Second stage would correlate the channels based on the geographic positions of the sensors, and it would be trying to make sense out of the transmission of sound waves in the Earth. So this next slide is the algorithm. This isn't my slide. I'm not a seismologist, so I don't know what A and F means, and I don't know if this is a standard algorithm or if this is something cooked up ad hoc. But you can see that it's very complicated and that it's not really signal processing. It starts off as signal processing, but it's been simplified and it's got some arbitrary parts to it. So it's basically it's a heuristic. I'm assuming that this wasn't discovered from the data, but that it's based on rules of thumb and the earth science. So if you look at this, it's very confusing. The very wiggly green line represents one channel of filtered data. And the invisible light blue line and the darker red line are sliding averages of this. The lines, the purple line ratio 1 and ratio 2, I think are ratios of these averages, but not point by point. One of them is clamped to a value in the recent past or across one of these thresholds. There's thresholds up and down so that you don't get a bang-bang, so that you don't get false negatives. You have to cross the higher threshold to get an on event. So some complicated number, I don't even think it's ratio 2, yet another derived time series has to cross these thresholds to find areas of interest. And then just to make it more ad hoc, there are certain extra rules about the length of an interval, which are to get rid of outliers. And for example, if the interval can't last, if the interval's too short, it's not plausible that it's an earthquake. If the interval's too long, it means we had to drop out and miss some data. So we were asked to try and implement this algorithm with our platform. In other words, we were asked to encode this in our application language, which is pretty standard SQL. It's SQL in the streaming context, so it was pretty strange. So what is SQL Stream? So I'll briefly explain what it's for and how it works. It's a platform for streaming analytics that is doing real-time computations on real-time data streams. So the peculiar property, its defining adjective, is that it's based on SQL. But it's SQL in a streaming context. And like all streaming systems, it's important to provide results continuously, as quick, and compute things as quickly as possible. The other characteristic is that we've tried to make it a scalable, distributed platform. In fact, while the current version is a client-server system, the next forthcoming version is a cloud version in which there's a central control node, but computation happens on several nodes with automatic routing of data for and redundancy and fallback, kind of the way most distributed systems do things. So if you were to look under the hood, if you would approach, you'd say this looks like a database, but it doesn't act like a database. And if you lift the hood, you'd see that part of it is a database, that we've got a query engine and a metadata catalog the way that a database does, and our language is SQL. So like a database, we take a declarative approach. We have a persistent store of metadata describing things, but the difference is that with a standard database, the goal is to answer a question. So and usually you're running against static data of whether it's a small amount or it's a huge amount. You're computing a simple result. So it was interesting hearing about fish this morning. The difference with that is that where that seems to be a tool for a programmer to generate a distributed streaming system from a small piece of code, an algorithm, ours is more like a programming environment that runs on a server, exists, and one does applications against it. It's designed for performance. It appears to be a database it talks JDBC and SQL to clients. And it's also been designed for extensibility. It's based on a very flexible query engine. So it's possible to integrate it with external systems and to put in plugins to run code that's not SQL and not even Java. So conceptually, what we've done is apply database technology to a stream. So the difference with other systems is that a stream for us is not simply a sequence of messages. It's a sequence of time-stamped, strongly typed rows. And when we evaluate things in a streaming, an expression on a stream, we get a streaming result. And we've tried to stick very closely to standard SQL. It turns out that there are a few constructs which have a natural streaming interpretation. But when something is, so we do the usual things of computing scalar functions, database operations, and we also can compute analytical functions on sliding windows. So actually what would happen is that if you designed a system as a series of SQL queries, they're compiled to be query plans, but the plans are turned into a data flow graph. So actually we're using SQL as a way of constructing, declaratively defining and constructing a data flow graph such as this one. So this is meant to show, here we have 2 inputs and three outputs. And the green blobs are named streams. So that's something like a topic in a message passing system, but it's more strongly typed. A stream is an infinite series of rows of a particular type. And the cool thing is that this graph is dynamic. It's possible for this to run a very long time and to add and subtract new queries from it. So you might have a long-running system that defines S1 as some signal of interest, and then you might later add a secondary query to ask about some other calculation at S2. So the little gray boxes are doing calculations, and the green streams are merging their inputs and multiplexing their outputs. So it's been designed for speed. The distributed architecture that's coming out soon is designed to scale. So here, the graph is distributed over several nodes, which communicate over our own binary data protocol. And this is designed to both for redundancy and for partitioning the data set. You automatically split up the data based on a key value of some field. So now I'll talk about briefly about the specific application, which was to encode this rather strange algorithm in SQL and to integrate into this existing infrastructure. So as I mentioned, the infrastructure is based on AMQP. We were replacing a small handwritten Python program to do this calculation. So the first question is how to deal with signal processing data as typed streams. So basically, we've got a time series of a vector x of t, various quantities, and I represent that as a stream of rows, each of which has the components of x, which are in different dimensions, as fields, plus the actual time as a timestamp. And we merge all the channels into one stream, which I call a wide stream, because it could be a virtual stream. We can subdivide it later automatically in distributed processing. And the trick in doing this in SQL is that you don't have local variables. So as you calculate things, you just compute additional columns. You have more and more columns. And then finally, you do a projection at the end to give the results. So let me just show this. So this is an overview of the data flow. And it's straight through. It's one pipeline. A message packets come off the bus. They're decoded to be actual vector blocks of sample data on one channel. They're filtered. Then various computations are applied, some of which are straightforward applications of existing SQL operators like average, and some of which required some extension. But we have the facility to add operators and transformations written in Java, written in SQL, written in C++. So I've identified the elements that weren't well supported in SQL, and I made prototype implementations of those. And we might find that if these are important analytic operations on streams of this type, that we would incorporate them as built-in things. Then finally, you get to the complicated calculation. You've computed all those averages, you've detected all the transitions, you've matching up transitions and down transitions. You've rejected the pairs that are the wrong size or violate some of the other conditions. You finally have detections. And then when we have the detections, we just put out a simple message. Actually, what we did is the requirement was to match an existing system that simply output a little text record when it found something. But you can't really tell if that's right or wrong. It was more dramatic to add where I have the second blue blob there, detectors. That's another stream, and because it's a stream, after running this pipeline, I could hook in another query to pull off that, a query that could compute the throughput of the system, or a query that could graph the results. In fact, the graphs that I showed earlier are actually the graphs of our system producing the correct result, and they were made by having a streaming query and having it write a table and using something like MATLAB or Octave to graph it. So I could go into more detail about how this works. The gist of it is that as you go down the pipeline, this shows the row type as it increases. Oh, sorry, I've skipped one. So as the data is acquired and processed, each horizontal line represents one row of data, which is one sample. And it not only does it have a timestamp and certain input values, as it goes down the pipeline, the computed values become more and more columns. That's a workaround for the defects in SQL as an application programming language, that it doesn't have local variables. But by doing everything in SQL, we're actually doing it very efficiently. Because I should emphasize that although we speak SQL, and although we use database technology, in that we have a query planner and execution, our execution is completely unlike a database. It's the opposite. We're avoiding disk. We're dealing with incremental computation of data on the fly. We try to do computation in local memory, and when we're distributed, we're using our own SDP protocol to stream data as quickly as possible from node to node, or between clients and nodes. So once a query is set up, you're not even talking to the control node. You have a direct pipeline to data. It's basically a rapid computation of large throughput data streams, also trying to minimize latency. And when you are reading a result set, the results from a query, essentially results are being pushed at you. So in conclusion, well, I mentioned the scaling up. I personally wrote the SQL code I haven't bothered to show you to work on an initial prototype of just 10 channels. But this same code was used in a demo prototype of, I think, 1,000 channels that could scale up to 14,000. And this required no change in the code because of this idea of natural, well, the problem is intrinsically parallel in that all the channels could be computed in parallel. So by making one large stream in which one of the tags is the channel ID, the problem can be split up and distributed over various nodes and then recombined. And our forthcoming distributed system does that intrinsically. But for purposes of this prototype, a year ago, we were able to run kind of a federation system using a simple cloud resource manager, which on demand provisioned and started, I think, about a dozen of our servers and divvied up the inputs and collected the outputs back again. And so the reason we're able to do that is, well, of course, partially because each individual node is efficient enough because the processing is this compiled data graph. And the other reason is that it was very easy for us to hook into to deal with the resource manager and to deal with the message bus because we are flexible enough to have adapters. So to conclude, I hope I've shown that our platform is extensible and interesting. It's a commercial product, but we're very interested in unusual applications and in research applications, since that's the way we can keep up with the way the world's changing because of the availability of all streaming data. And so we're very interested in working with academic and other researchers, and a research license would be available probably by arrangement for nothing or for free or for a nominal charge. So if anyone's interested, please speak to me or email me at sqlstream.com. And that's it.
Thank you very much.
Oh, thank you.
So along those lines, I have a question.
Yeah.
Could you give us a broad picture of who your customers might be? Who are you targeting? How does your infrastructure scale? And so what problems would this be best suited for? What problem domains?
Well, in scaling, we are working on dealing with, we can easily deal with 30 or 40,000 rows a second. We're trying to go higher to 100,000 rows a second. Now, what is a row? Typically, a row is fixed size message of from 40, 100, maybe half a K. It has to be strongly typed data for the relational approach to pay off. And in the history of the company is that we're not experts in machine learning. So we are looking for customers, we're looking for applications that would benefit from timely results and have a large amount of real-time data. But we are helping them encode their application in SQL and trying to stretch SQL to encompass their applications. I'm also very interested in applying some of the standard and new algorithms in machine learning, especially the machine learning on streams that I've been hearing about today. Because with some of our applications, like one thing that we're doing is monitoring and predicting road traffic in large metropolitan areas. And here there's, because of the prevalence of GPS and sensors on roads, there's more and more data available all the time. But we've been kind of ad hoc in how we were going to interpret this to produce interesting results. So I think that there's a very fruitful juncture between the commercial world that maybe is jumping from database technology to streaming technology, and these interesting offshoots of artificial intelligence. But you asked me about clients.
Okay.
Yeah.
Thank you. We have time for one or maybe two more questions in the audience.
So you mentioned that this works with a network of sensors. You had the image of the U.S. with a bunch of points on it, different seismic sensors, and are all the readings for those sensors contained within one row during operation, or is it one sensor is one data stream, data flow?
Well,
somehow combine them?
Right. I guess I rushed over that. Each data point, each is a row, where by data point I mean a timestamp, a channel identification, and various attributes of data. These are probably each X, Y, and Z signal is a separate time series. So basically, a time series is a triple: a label, a channel label, a time t, and a value. So that would be one row, because the row is it's simplest to do scalable computations on a single row, and to do comparisons and aggregations on a window of adjacent rows.
Then once you process that single sensor's collection of 3 readings, how are those combined together? Or are you
that was a separate phase, and I was kind of perplexed that they asked us to do this, probably to make us go away, this scalar computation rather than do that. There's a second phase in the prototype application that compares neighboring sites in geographically neighboring sites. But I think the emphasis of the overall OOI was to combine lots of different grids, which have very heterogeneous data sensor types, and to standardize the data formats, and to provide a platform for computing. Oh, there's I think a question in the back.
Okay, yeah.
It's not in-memory database, right? Is it?
It's in memory, but it's not a database. It's similar, but the focus isn't on storing a large result in memory. It's on dispatching the rows very quickly. It sort of approaches that if you have very large windows. If you need to do exact computations over the past day or month, you'd be storing a lot of results, and that's kind of like a table in an in-memory database. But the focus on, in terms of features and optimization, is just sort of pushing the data off the node as fast as possible.
I think this is very cool stuff. We're about 8 minutes behind schedules, which is pretty good. Please, if you have any other questions, take them offline.
Oh, please.
Let's thank the speaker again.
For describing the computation, and as an experiment, we were just asked to help build a little piece of this. I think what was happening was that there was an existing system using proprietary software, and they were trying to detect earthquakes, and they wanted to adapt this to fit into this generic infrastructure. And so we proposed that we could help do it. So now, quickly into the background of the application. The general point is to detect meaningful events in seismographic signals. And eventually there'll be a large worldwide system of sensor grids of all different kinds, mostly on the ocean floor. But at the time that we built this prototype, what was available is this array of ground sensors. So I don't know if this is accurate or just suggestive, but there's a regular grid of ground stations which have seismographs, and each of these has at least one sensor that we did with a consortium of universities, specifically UCSD. So I'll briefly give the background and sketch out the problem, and then I'll spend about half the time talking about SQL Stream, explaining what it is and what it does, and then I can go a little bit into the details of the solution. So I'm kind of an outlier here today because I'm not talking about machine learning at all. I'm talking about infrastructure, a specific programming platform for doing computations on streams on a single client server system or in the cloud. So the background is there's big science. There's a large consortium called the OOI, Ocean Observatories thing, NSF founded, involving various institutions, academic institutions in the country. And the idea is to provide a kind of enormous cloud workspace for fostering research and publicizing the results of research. And a little piece of this is called the OOI-CI, which stands for Cyber Infrastructure. And it's basically a private cloud that's being built up so that experimenters can share data and share networks of sensors and provide an application computing platform for doing stream computing. So here's their slide, and it's much better than anything I can draw. And you can see from the logos at the bottom that this is well sponsored, a lot of institutions involved, and it's very large scale. So a lot of work's going, it's a long-term project, and this infrastructure is being built up. Well, we got involved doing an application to plug into this about 1.5 years ago. So at that stage, there weren't many tools to make this an easy thing to build an application on. There are the usual open source components are available. There's great use of AMQP, which is an open source message bus with a Java bias. And a lot of the experiments are done by just experimenters writing their own Python code. Well, where we're coming from in our company is we're trying to provide a kind of a middleware platform where it's easier to develop streaming applications. Now, our focus is really on the commercial world, and our particular take on this is that SQL, the database language, is familiar to commercial applications, and they would be in the situation that they would have some kind of batch-oriented database application, and they just couldn't cope with the new world of streaming data. So this would be an easy transition for them. Nevertheless, we met people some scientists who were working on a project here. So I'm looking at our platform more abstractly, that we have a higher level language, some of our abstract for.
Our next speaker is Mark Berkowitz, who is from SQL Stream Incorporated. He's going to be talking about infrastructure for the streaming data problem. Lots of us machine learners who are working on streaming problems could make use of some of the infrastructure, I think. Seems like a pretty cool product. His background is he got his bachelor's in physics from UC Berkeley, and he worked in the financial industry for a while. And without further ado, please tell us about SQL Stream.
Thank you, and thanks for inviting me to this conference. So I'm an engineer at SQL Stream, the company, which makes SQL Stream the product, which is a platform for streaming analytics. But I'm going to be talking about a particular application of this, in seismology, specifically a joint project that